All right. So let's continue then. So we were talking about matched filters, and a matched filter is matched to a particular pulse. So if we say that a filter which is matched to H has an impulse response which is a complex conjugated time reflected version of it. So if H looks something like this, then the matched filter would look something like this. So it's basically you take the signal and you flip it, time reverse it, and then you have the matched filter. Okay, if it's complex signal, you also need to complex conjugate that. But that's the thing that needs to be done. And then I claim that if we have a particular input R to a filter which is matched to a pulse H, then we get an output, obviously, right? You always get an output. But if we sample that output at time equals 0, then the sample is the inner product between R and H. So let's just motivate why that is the case. So we have a situation here like we have an input R, and we have a filter whose impulse response is matched to H. Okay, so again, it's conjugation of H and then time reversal. Then we get some output Y. We sample that at time t equals 0, and then we get a number. Let's call that Y, which is then, of course, equal to the signal Y at time 0. Okay, so what is Y? Well, it's it is the convolution between R and the impulse response. So it's R convolved with F, where F is equal to H conjugate negative T, like this. Okay, now I know, since the back when I learned convolution, that there is a lot of confusion around these things, and some unnecessary mistakes can be done by just simply writing up this integral in the wrong way. Okay, so we see here we have two signals which produce a third signal, right? So of course there needs to be some dependency in this integral on R and F. Okay, there also needs to be some dependency on T, because T, this is a signal. This integral here should be a function of T, right? The left-hand side is a function of T, then the right-hand side should also be that. Okay, so it needs to have R and F. So it's R and then F, like this. And then it's an integral. Okay, so now is the tricky part. What should be inside the parentheses here? Okay, there must be a T somewhere. Okay, and then since an integral here, we also need to have some dependency on the integration variable. Okay. So my first thing to recommend here when writing up convolutions here is to pick your favorite integration variable. Okay, the only choice which is not a good choice is to select T. Okay, integrate with respect to whatever you like, but not T. I like U, okay? And therefore I put in U here. If you don't like U, select something else, right? Okay, the next thing we need to figure out is what should be inside here. Okay, and here basically just learn this, right? And first, I usually just take the first, the integration variable and put that into R here. Happens to be the first one. And the other one should be, okay. And here's the tricky thing now. Should it be U minus T or T minus U? It should be T minus U, like this. Okay. T here, U, U, U. Right. Bulletproof if you do it this way. Okay. Do it some other way on your own peril. Okay. Now, so what makes this a little bit tricky? Okay, so let's continue then. And what we're interested is in y evaluated at time t equals 0. Okay? And that's easily done from this by just putting in t equals 0 here. So what we have here is now an integral from minus infinity to infinity r of u f of minus u du, like this. Okay. Notice that there is of course no t dependency left because we have fixed t to be equal to 0. Okay, and now what is this? Well, then we select this relationship. We know that f of negative f of t is equal to h conjugate negative t. If we replace t with u, we see that f of u is h conjugate negative u. And then it's not hard to convince oneself what stands inside here is h conjugate of u. Right? We change the sign of the independent variable and we conjugate. Okay, and here we then have the integral from minus infinity to infinity r of u h conjugate u du. Like this. Okay, and by definition, this is what we call the inner product between the signal r and h. T. Thank you. Okay. If r of t is h of t, then the output y is what? It's the inner product of h with itself. Do you remember what that is? The inner product of a signal with itself? I heard the norm squared. It's the energy. Okay. So it's the energy of the signal h. E for energy and then subscript for the signal that we're looking at. Okay, so now back to the problem we're dealing with. We would like to say something useful about this this receiver. Okay, so we have pulse amplitude modulator transmitter, some transmitted signal, some noise, received signal like this, and then we start by having a matched filter, and the filter is then matched towards the pulse that we use at the transmitter side. Okay, and then we get the signal y, and we sample that once every t seconds, and then we get a sequence of these y's. Now, I claim, and we will soon see why this is true, that y OK here is equal to the energy of the pulse h times a of k plus noise. Okay. So this thing here is some type of amplification. This is the diagram here, this triangle here is an amplification with amplification 1 over EH. So Z of k is just A of k divided by the energy of EH. Okay. So basically here, this device only divides by EH. That's what it does. Okay. So let's look at this receiver a little bit. So we should analyze it a little bit. And what I'm trying to, at the end, or what we should arrive to, is that whatever we get here, the output of this device we haven't talked about yet, so I don't know, I will explain it in a second. But anyways, the output here will be our guess on the transmitted symbol A. Okay. Okay. Yeah. So let's look at this a little bit. Okay. So let's consider the transmission of the first symbol. Okay. What do we mean by the first symbol? So here we have a sequence of symbols, A0, A1, A2, and so forth. Let's just look at A0, okay? The 0th symbol. And hopefully what we would arrive to is that this is a minimum distance receiver decision on A0. That's what we want to do here. So consider transmission of A0. So when the transmitted signal S of t is A0 times H of t. Okay. So this is the pulse which carries A0. Okay. And then we have a bunch of other pulses, but this is what we consider right now. Okay. Recall that there is a mapping between symbols and bits. Okay. So for example, it could be something like this, that we have 2 bits in, which then gives 1 symbol out. So what are the possible input patterns? Well, it's 0, 0, 0, 1, 1, 0, 1, 1. 4 in total, 4 possible input patterns. This could be represented, this bit pattern 0, 0 could be represented by a number from 1 to 4. So 1, 2, 3, 4, this is M. And then A0, the symbol that we transmit, will then be some amplitude A1 if we transmit the bit pattern 0, 0. A2 if it's 0, 1, A3 if it's 1, 0, and then A4 if it's 1, 1. And the transmitted signal, which is A0HT, would then be S1, which is A1 HT, S2, which is A2 HT, S3, A3 HT, and S4, A4 HT. Okay. So this table here represents how bits, signal alternative index, amplitude or symbol, and transmitted signal are connected. So these are 3 or actually 4 different facets of the same thing, right? So if we want to transmit 0, 0 bit, the bit pattern 0, 0, we transmit the symbol index 1, or the amplitude A1, or the signal A1 HT. That's how it's connected, right? So these are 4 representations of the same thing. And they are useful in different contexts. Okay, so now what we would like to then is that if the receiver, if we go through this interval here, we would like that zk is equal to ak. I think there is a mistake here, of course, so it should not be ak divided by eh. It should be yk divided by eh. Sorry for that. Okay. So let's do a small sanity check whether this block diagram makes sense. If we don't have any noise, it better be such that the input to the decision device here is actually what we transmitted. So when n of t is equal to 0, we should have that z of k is equal to ak. Let's see that this is the case. So what is so we do this, we look at A0, how it goes through the whole thing here, and look at what Z of k is. So Z of k is Y of k divided by EH. Y of k is the inner product of the input with the pulse H of t. So Z0 and let's go with Y0. It's the inner product of R and H of t. Okay. Why is this the case? Well, it's because the input, when noise is equal to 0, is the transmitted signal. And what is the transmitted signal? Well, it's A0 times HT. And then it should be the inner product with H. So this is equal to A0 H of t inner product with H of t, like this. We can take out A0 from this, and then we have H of t inner product with itself, and we're left with A0 times EH. Okay, and then Z0 is 1 over EH times Y0, which then becomes equal to A0. Okay, so that's fine. This first part of the receiver seems to be reasonable in the sense that if we see how A0 travels through the block diagram here. So for A0, the output is A0 times H of t. And then if we forget about the noise, this is also equal to the received signal. The output from the received signal, the output from the matched filter, when we have a matched filter which is matched to H of t, is then R of t, H of t, like this, which happens then to be equal to A0 times EH. It becomes a little bit messy now, but then we simply take this and we divide through by EH, and then we get Z0 equal A0. Okay. So in the noise-free case, the input to this slicer device here is equal to what we transmitted. That's what I'm trying to say. Okay, so that's fine. That's great. Now, this is true in general if we also see a sequence of AK here. If H convolved with the impulse response here is a scaled Nyquist pulse. So then there is no intersymbol interference between the different pulses here. So the block diagram here is fine when there is no intersymbol interference. So if we select H and H conjugate here such that it's a scaled Nyquist pulse, then we're fine. Okay. Now, unfortunately, it's never the case that noise is equal to 0. Okay? If that would be the case, then there would be no problem in the physical layer, but noise is not equal to 0. So what happens if we have noise here? Well, so in the noisy case, so when n is not equal to 0, then Z0 would be then A0 plus some noise. Let's call it N0. This. So we will not receive exactly what we transmitted, but what we transmitted plus some disturbance, this noise. Okay? So the input to the slicer, the input here will not be exactly what was transmitted. It will be that what was transmitted plus some noise disturbance. And the objective of the last device here, which is called the slicer, is to output the symbol which is closest to the input. Okay. So they output the symbol in curly A, the symbol alphabet, that is closest to the input. So if the input is A0 plus N0 into the slicer device here, the output, which is our guess on what A0 is, it is equal to the arg min of the difference between the input and possible elements in the symbol alphabet here. Maybe an example will clarify the main idea here. So suppose that curly A here is the possible amplitudes, -3, -1, 1, and 3. Okay, so the first one here is A1, second is A2, this is A3, this is A4. Okay. So we have 4 possible amplitudes, -3, -1, 1, and 3. These are the 4 possibilities. Then we have some input to the slicer device, which is Z0, which is whatever was transmitted plus some noise component. Okay. And if the noise was 0, we know it's going to be either -3, -1, 1, or 3. These are the possibilities. So if this is the possible transmitted amplitudes, and we receive an amplitude here, what is a reasonable guess on what was the transmitted amplitude then? 3, exactly. If it's here, what should we select then? -3, right? It's closer to -3. If it's here, Well, it seems like 1 is a reasonable choice, right? So we pick the amplitude which is closest to the input, and that's our guess. Okay. And we see that there are some boundaries between the signal alternatives here, -3, -1, 1, and 3, where we are inside this interval here, we're closer to 1 than to any other signal alternative. So when we're inside this interval here, the output of the slicer should be 1. Okay, so now we have defined what the output should be when the input is in here. If the input is beyond 2, which is in the midpoint between 1 and 3, then the output should be 3. Okay, it's not drawn to scale here, but I think you get the idea. Okay, and on the negative side here, we should do exactly the same thing, but the opposite. So inside this interval from -2 to 0, the output should be -1, and to the left of -2, it should be -3. So this is the slicer operation. For any input, any number in, it outputs 3, 1, -1, or -3. These are the possibilities. And it selects the point which is closest to the input as its output. Okay. Another way to illustrate this is to simply have a straight line due to space constraints. I'll put it here. So again, we have some input here, Z0. And then we put up the points here, -3, -1, 1, and 3. And we put in the decision boundaries, is the midpoints between adjacent points, like this. And then we define regions for all possible signal alternatives here. So -3 is all the values on the axis, which is to the left of the decision boundary. Okay? All of these points will be mapped to the output -3. The middle part here, from -2 to 0, will be mapped to -1. From 0 to 2, this will be mapped to 1. And then finally, all parts to the right here will be mapped to 3. Okay. So this is called the decision region. For let's call it A3. Sorry, A. Which one is it?
A1.
Yeah, so maybe we should call it just A hat is equal to -3. That's the output, right? So, okay. So to define these decision regions, we have one region per possible amplitude. Okay, and in this case, we had 4 different amplitudes. Okay, so let's see where we are. We're doing pulse amplitude modulation. We do matched filtering. We sample the matched filter. We divide through by the energy of the transmit pulse to get Z of k equal to A of k when there is no noise. So Z of k will be equal to for the zeroth symbol, it will be Z0 will be equal to A0 plus some noise. If the noise is not there, it's easy to make the decision. When the noise is there, we need to somehow select one of the possible values of A0. Okay? And what we do then is we pick the symbol, the amplitude that is closest to the input. Okay, so that's what the slicer does. And I claim that overall, this structure, consisting of a matched filter, sampler, scaling factor, and a slicer, is a minimum distance receiver for pulse amplitude modulation. Okay. And that's the best we can do. Okay. Any questions? Okay, so this is the principle that most receivers are built upon, and also the principle that you probably want to use in your project when designing such a system. The caveat for this is, of course, that H of T should be selected wisely so that there is no intersymbol interference. Because if there is intersymbol interference here, this is not a very good receiver structure. Then we need extra processing on top of this, but that's outside the scope of this course. Okay, so that is in some other course. Right? Okay, now let's talk a little bit about how this is done also in practice. We haven't said much about the pulse H here, rather than it should be something which is a Nyquist pulse or root Nyquist pulse. But there is a difference between pulse amplitude modulation in baseband or in passband. And if it's in baseband, then the power of the transmitted signal is centered around 0 DC. Okay? And this is typically fine for cables, like Ethernet and things like that. But if we want to do this over radio, over high frequencies, we need to move the spectrum of the transmitted signal to be around some high frequency. Okay. So, for instance, for Wi-Fi or something like this, this frequency could be roughly 2.4 gigahertz. Right. So we would like to put the transmitted signal around 2.4 gigahertz. The bandwidth of the signal, however, for Wi-Fi is approximately 20 megahertz for the most common type of Wi-Fi. There are other, 10, 80, and 160, and so forth. But for the vanilla Wi-Fi, it's 20 megahertz, like this. Okay. So what is typically done in real implementations is that the baseband process is first created, and then it's moved up to frequency through a circuit that simply takes the baseband signal and multiplies that with the cosine carrier, where the cosine carrier has a frequency which is the mid-frequency of your choice. Okay. So now, if we do this, it turns out that the spectral efficiency is not very good. Okay. And the reason for this is that when we have a definition like this, A here is a real valued number, okay, and we see that the bandwidth here, we have a factor of 2 of the transmit. Okay, let's start again. The bandwidth of the transmitted signal is twice the bandwidth of the baseband signal, and we said that we wanted to conserve bandwidth here. So this seems to be a bad idea to move it from baseband to passband like this. Now, luckily, it turns out that we can actually we can regain this loss of a factor of 2 by transmitting data on a cosine carrier and a sine carrier at the same time. Okay, so let's see how that works. So this is a little bit of a busy slide, but let me go through this. It's actually not so complicated. Okay. Again, we have some bits, and we would like to convert that into a signal. Okay, that's the modulator part. Now, the signal here, we would like that to be centered around some carrier frequency. Okay, 2.4 gigahertz if it's Wi-Fi, say, or 5 gigahertz if it's that type of Wi-Fi. But anyways, so what we do then is that we have selected some center frequency of the carrier, FC, and we take our bits and we produce then symbols, and then we take a symbol and we split it into two parts, one that goes like this and one that goes like this. If we follow the top branch here, we see here we have some amplitudes that carries bits through this device. So this carries some bits, and then we feed it through a pulse amplitude modulator with some pulse shape that we have chosen, a root Nyquist pulse of some sort, and we'll multiply that with a cosine carrier, and then that forms half of the transmitted signal. The bottom branch here is exactly the same thing, except now the difference between the top branch, where you have a cosine carrier, and the bottom branch is that in the bottom branch we have a sine carrier. But we see they have the same frequency, it's just one is a cosine and one is a sine. Okay, so our transmitted signal here is the sum of two branches, one with a cosine carrier and one with a sine carrier. Sometimes this is called the in-phase branch, and this the quadrature phase branch. It's not super important at this point why it's called like that. Okay, good. Now the problem is that can we, given an observation of S, can we somehow separate this so we can figure out A here and A here independent of each other? And that turns out to be the case. So the receiver looks something like this. Okay, so here we have this transmitted signal, we have some noise, and here's the receipt signal. And then we split it into two branches. One branch on the top here, which is the in-phase branch, where we have a cosine carrier, and then a bottom branch where we have a sine carrier. Otherwise, they're identical. And what happens in the top branch, if we go through this, we multiply with a cosine carrier, we have a matched filter, which is matched to the pulse that we had at the transmitted side. We sample that at once every t seconds, and then we get a z, just as we had before. It turns out then that this is equal to AKI. And what is AKI? Well, that's the input to the top branch here. It will be equal to AKI if noise is equal to 0. Right? So, I mean, noise will always perturb this a little bit, but we see here that this part has nothing, is not disturbed by what is transmitted in the other branch. So what I'm trying to say here is that we can transmit two pulse amplitude modulation signals, one on the cosine carrier and one on the sine carrier, and they can be separated perfectly at the receiver without any crosstalk between them. And by doing so, we can transmit two PAM signals within the same bandwidth without any crosstalk. Okay, so going back to this, it looks like since the bandwidth of the passband signal is twice the bandwidth of the baseband signal, that we lost spectral efficiency with the factor of 2, but we can regain that by transmitting two signals in the same bandwidth here and separate those. So two signals, then we get back the spectral efficiency that we had from the beginning. Okay, so just to reiterate on this fact, this seems like a bad idea, but it turns out to not be a bad idea. Okay. Why am I bothering by talking about this is because these type of constellations now. Okay, so two things. The constellations we had when we had real valued symbols is on one line. But now, since we have one in the cosine carry and one on the sine carry, we can put them on two axes. And then we have points which goes along the in-phase branch and the quadrature phase branch here, and then we get these two-dimensional plots. And the regions here are the decision regions. So all the points here are closer to this signal alternative than to any other signal alternative. So when we make decisions, this is a decision we make. So when the received signal is in this region, we make a decision to say that this point was the transmitted one. Okay, and then one can have, as in this case, we have 2 bits along this dimension, so 4 possible signal alternatives along this one and 4 along this one. So 4 times 4 is 16, so we have 16 points like this. Means 4 PAM along a cosine carry and 4 PAM along a sine carry. We can also have, constellations which are not symmetrical. So here we have 4 along this axis and 2 along this axis. So just to show that this is actually used in practice, these are some constellations used in Wi-Fi. As a matter of fact, in Wi-Fi we are not using one particular constellation, we are using many constellations. And it basically depends on how close you are to the access point. The closer you are to the access point, the more signal alternatives we can use. The further away from the access point you are, the less you can use. So when you use Wi-Fi, you don't always get the same data rate. It depends a little bit on where you are. Okay. Questions? All right. So this was a pretty dense lecture. So if I should give you some advice on what to study, is to study this structure here to try to figure out why it works. Okay. Try to motivate this for yourself. What are the different components? Why are they designed as they are? And why does this work? Okay. The next lecture, what we will talk about then, is to go into detail. What is this mysterious noise? How can we model the noise? And from this model of the noise, how can we figure out what is the probability of error? And the probability of error is the probability that the output from the receiver is not what we transmitted. Okay? And obviously, we would like to control this. We would like to have as few errors as possible. Okay? And then we will learn how to compute this error probability. And then from that, from these expressions, we can figure out design choices. Why do we do it like this, and so forth. Right. But again, this was pretty dense, right? And but please have a look at this and try to figure out what it does. It will serve you well. Otherwise, we see each other on Thursday, and then there is another lecture on Friday. And don't forget to go to the startup meeting for the projects, because starting from Thursday, you should be in good shape to start to do part 1 of the project. And the sooner you start with that, the less stress you will have at the end. Okay, so see you on Thursday.